The internal combustion engine, a marvel of engineering that has changed our world forever. First developed during the Industrial Revolution, it caused several revolutions around the world, including the automotive industry and many more. In this video, we will explore the history and the inner workings of the internal combustion engine in order to have a deeper understanding of our world. The internal combustion engine is one of the most important inventions in human history, powering everything from cars to planes, but it didn't appear overnight. It evolved from centuries of experimentation with steam power, air pressure, and controlled explosions. Before ICEs, the world relied on steam engines, using boiling water to create pressure and drive pistons. In 1698, Thomas Savery built the first practical steam-powered pump. Then in 1712, Thomas Newcomen improved steam engines for industrial use. Finally, in 1765, James Watt developed a more efficient steam engine, leading to the Industrial Revolution. But why didn't steam work for cars? Well, steam engines are way too bulky and heavy. They also have very slow startup time, and finally they are not very efficient, which is a very important trait for applications in cars. In 1860, the two-stroke gas engine was created, the first ICE to actually power a vehicle. Then, in 1876, Nicolaus Otto invented the four-stroke cycle engine, known today as the Otto cycle, the foundation for modern gasoline engines. And from 1885 to 1886, Carl Benz and Gottlieb Daimler developed the first gasoline-powered cars, leading to the birth of the automotive industry and to Mercedes-Benz. Then, in 1892, Rudolf Diesel invented the diesel engine, which was more efficient than gasoline engines due to the higher energy density of diesel. In the 1920s, the mass production of cars started to take off, thanks to Henry Ford's assembly line, making ICE-powered vehicles affordable and a common sight. But you see, an internal combustion engine doesn't necessarily have to be a piston engine. There are multiple variations of the internal combustion engine which all serve different purposes, thus having a wide variety of real-world applications. But first of all, what exactly is an internal combustion engine? An internal combustion engine, or ICE, is a heat engine in which the combustion of a fuel occurs with an oxidizer, usually oxygen, in the air. In an internal combustion engine, the expansion of the high temperature and high pressure gases produced by combustion applies direct force to some component of the engine. The force is typically applied to pistons in the piston engine, to turbine blades in a gas turbine engine, a rotor in a Wankel engine, or a nozzle in a jet engine. This force moves the components over a distance. This process transforms chemical energy into kinetic energy, which is used to propel, move, or power whatever the engine is attached to. In this video, we will only be discussing the piston engine, the gas turbine engine, and the jet engine, due to their widespread adoption in a variety of industries. While there are many stationary applications, most ICEs are used in mobile applications, and are the primary power supply for vehicles such as cars, aircrafts, and boats. Reciprocating piston engines are by far the most common power source for land and water vehicles, including automobiles, motorcycles, ships, and to a lesser extent, locomotives. There are multiple kinds of piston engines. First, let's take a look at a generic piston engine, and then we'll explain each variation with more details. In this example, we'll be looking at a typical four-stroke engine. It's important to note that some of the parts that you see here may not appear in other variations of the piston engine. So a typical piston engine consists of the crankshaft, a metal rod which transfers the power generated by the engine to the transmission. The exhaust camshaft, a rotating shaft with lobes that control the opening and closing of the engine's exhaust valves. The intake camshaft, it's basically the same as the exhaust camshaft, but for the intake valves. The pistons. The piston is responsible for transforming the force exerted by the expanding gases generated by combustion into linear movement. The connecting rod. As its name says, the connecting rod connects the piston to the crankshaft, transforming the linear movement of the piston into circular movement. The spark plug. The spark plug generates a spark, causing the sudden combustion of the air-fuel mixture. It's important to mention that diesel engines work without spark plugs. The water jacket for coolant flow. This is crucial for maintaining the temperature of the engine. And finally, the valves, allowing the exhaust and intake to take place only when it's required. As previously mentioned, piston engines come in various types, with the main ones classified into 4 distinct categories. First of all, there's two-stroke engines. The two-stroke design simplifies the engine by completing its power cycle in two piston strokes, one up and one down movement per crankshaft revolution. This is done to increase power output but leads to lower efficiency and consequently more emissions. Two-stroke engines are known for their simpler design, which makes them lighter and easier to maintain. They can pack a lot of power into a small space, making them suitable for applications where lightweight and high power are needed. Unlike four-stroke engines, two-stroke engines don't rely on valves for intake and exhaust, instead using ports in the cylinder walls as seen here. Finally, two-stroke engines require pre-mixing oil with fuel for lubrication, as they don't have a dedicated oil pump. But how does this simple design work? Well, first we have the compression stroke. Here the piston rises, compressing the air-fuel oil mixture in the cylinder. As its name says, there are only two strokes in one full cycle. In the power stroke, the compressed mixture is ignited, causing the piston to move downward, generating power. The exhaust and intake take place after the piston moves down, exposing ports that allow exhaust gases to escape and fresh air-fuel oil mixture to enter the cylinder. Two-stroke engines are commonly found in applications like lawnmowers, chainsaws, motorcycles, and smaller outboard motors, but they aren't that common in cars. Then there's four-stroke engines. As its name says, here there are four strokes, each responsible for either intake, compression, combustion, or exhaust. This design makes the four-stroke engine inherently more complex, needing valves, valve camshafts, and oil pumps, in order to have the correct timing for each step of the full cycle. As mentioned before, there are four steps. The intake. Here, the piston moves down, increasing the volume of the cylinder and allowing for the air-fuel mixture to enter the cylinder. The compression. The piston moves up, compressing the air-fuel mixture. The combustion. The spark plug ignites the air-fuel mixture, causing a sudden expansion, which pushes the piston down, generating power. And finally, the exhaust, where the piston moves back up, expelling the burnt gases from the combustion chamber through the exhaust valve. Four-stroke engines are mostly used in cars, trucks, and some motorbikes. Modern automobile engines use computer-controlled fuel injectors to adjust the fuel-air ratio to maintain high performance. The four-stroke design is not only more efficient, but more durable and thus more reliable. The other two categories in which engines can be categorized are gasoline or diesel engines. Most diesel engines operate with a four-stroke cycle, the only difference being they don't use a spark plug for ignition. They instead compress the air to high temperatures and inject the diesel into it. Diesel engines are known to produce a large amount of torque, which is why they are widely used in the towing and hauling industry. They are also much more efficient than gasoline cars, meaning they can get further with the same amount of fuel. On the other hand, there are gasoline cars. As we saw earlier, they do use spark plugs to ignite the air-fuel mixture. You might be thinking right now that diesel engines have the upper hand against gasoline cars. I mean, they are more efficient, more durable, and have more torque, but we still haven't talked about those juicy horsepower. Gasoline engines commonly have higher peak horsepower, producing higher top speeds and acceleration. You see, we can calculate the horsepower of a vehicle with only two values from it. The formula goes as follows. Horsepower equals torque times RPM divided by 5,252. As you can see, the horsepower of a vehicle is dependent on two values, torque and RPM. And while diesel engines have the upper hand on torque, gasoline engines can usually rev much higher due to their shorter piston travel distance. This makes gasoline engines much more better suited for sports vehicles. And then there is also emissions. Historically, diesel engines have had much higher emissions than gasoline engines, leading to scandals such as the Volkswagen emission scandals, also known as Dieselgate. Now, let's talk about the turbine engine, shall we? The turbine engine, also known as gas turbine, is a type of internal combustion engine that uses a turbine to extract energy from a fluid flow. Typically, hot exhaust gases to drive a shaft and produce power. But how does it work? Well, first there is air intake. A turbine engine begins by drawing in air from the environment. Air is then compressed, typically using a compressor, increasing its pressure and temperature. Fuel is then injected into the compressed air and ignited, creating a high-energy exhaust stream. The hot high-pressure exhaust gases expand and pass through a turbine, causing it to rotate. The rotating turbine is connected to a shaft that can be used to drive other components, such as a propeller in a turboprop engine, a fan in a turbofan engine, or a generator in a gas turbine engine. The remaining exhaust gases are then expelled through a nozzle, generating thrust in jet engines. Turbine engines are the primary propulsion system for most modern aircraft, including commercial airliners and military aircraft. Gas turbines are also used in power plants to generate electricity. Turbine engines are used in various industrial applications, such as powering pumps, compressors, and other machinery. These engines are known for their high power output relative to their weight, and are generally more efficient than piston engines, especially at high speeds. Turbine engines operate on a continuous flow of air and combustion products, and their turbine's rotary motion allows for efficient power extraction and transmission, unlike piston engines, which have to transform the linear motion of the pistons into rotary motions. Finally, we've arrived to jet engines. A jet engine is a type of reaction engine discharging a fast-moving jet of heated gas, usually air, that generates thrust by jet propulsion. While this broad definition may include rocket, water jet, and hybrid propulsion, the term jet engine typically refers to an internal combustion air-breathing jet engine such as a turbojet, turbofan, ramjet, pulse jet, or scramjet. Air-breathing jet engines typically feature a rotating air compressor powered by a turbine, with the leftover power providing thrust through the propelling nozzle. There are many types of jet engines. We won't cover them in detail because that's outside the scope of this video, but some of the main ones and their main characteristics are the turbojet engine, with its pure jet propulsion, efficient at high speeds, and used in supersonic jets. It's used in military aircraft like the Lockheed SR-71 Blackbird. Then there's turbofan engines, being the most common in commercial aircraft. It features a large front fan that increases efficiency and reduces noise, used in airliners like the Boeing 747 or the Airbus A380. The turboprop engine uses a jet engine to drive a propeller, ideal for short-distance flights. It can be found in regional aircraft and cargo planes. Then there's also the turboshaft. It powers helicopters and some military vehicles. It can be found in aircraft like the Sikorsky UH-60 Black Hawk. And finally, there's the ramjet and scramjet hypersonic engines. They work at supersonic and hypersonic speeds by compressing air without moving parts. They were used in the experimental jets like the NASA X-43. That wraps up our deep dive into internal combustion engines, from piston engines powering cars to turbine engines in helicopters, and the jet engines that push aircraft to incredible speeds. If you enjoyed this video, don't forget to like, subscribe for more deep dives into automotive and aviation tech, and turn on notifications so you never miss a future upload. Thanks for watching, and we'll see you on the next one.